can see my screen, full screen?
Yes, we can see your screen. It's great, and we can hear you as well.
Perfect. Okay. Good morning, everyone. Firstly, thank you for this kind introduction and the possibility to present my study despite this current situation. My name is Khayyat. I'm a PhD student at Institute for Multiphase Processes at Leibniz University, Hannover, Germany. Today, I'm going to talk with you about the cryopreservation of water-based suspension by the floating process of blood storage. So let's start. Everyone knows that blood is quite important fluid. And in regard this, the blood supplies our blood with nutrients and oxygen. It also transports metabolic waste products and heat. In addition, it keeps the concentration of dissolved substances, the temperature, and the pH value almost constant. So blood is extremely important for us. But the question here is why the blood is frozen, stored, and then thawed if needed in specific cases. The shelf life of blood-containing products at 4 degrees Celsius is a maximum of up to 49 days. Then the existing blood will be disposed. In the UK, large quantities donors' blood are decreased due to the stability problems, and blood stocks for transfusions are seldomly sufficient for more than a week. In addition, the German Red Cross reported that because of COVID pandemic, the number of blood donors has dropped significantly in many parts of the country. So it's very difficult to get blood donors for a serious operation, for diseases, and for covering shortages, especially in civil and military emergency. In recent years, a wide range of methods for the cryopreservation of red blood cells has been developed. This include, for example, high cholesterol slow freezing, low cholesterol rapid freezing, and or other methods. These methods are usually used for the cryopreservation of closed container, such as blood bags. These bags, these containers, do not allow ideal heat transport. This leads to inhomogeneous and low cooling rates within the containers. To compensate this, large amount of cryoprotective agents must be utilized, some of which are time-consuming to wash out with specific and special equipments. Additionally, most of CPA, as you know, are toxic. So let's have a look at a very simple example of how the volume of blood bag looks like. We can calculate the heat flow by this heat transfer equation. A stands for the surface of the sample. When we increase the surface, we can increase then the heat flow. That means we can increase the cooling rate here. Both samples have the same volume, but the flat one on the right, as the surface is nearly 3 times bigger than the surface of the blood bag. So the heat flow of the flat one is nearly 3 times bigger. So if we don't use blood bags, we could increase the surface and the heat flow by creating a very flat sample. This would increase the cooling rate, and we would probably need less cryoprotective agent. The development of a new method, float freezer, for the cryopreservation of blood has already been started in our institute on the basis of a PhD thesis. This is based on the cryopreservation of blood without using a blood bag during freezing. The method is based on the principle of the float process, the worldwide process for producing flat glass. Here, the blood floats on a bath of cold bare flow carbon, so that blood floats on the BFC and spreads to form then a thin layer within a large surface area. Then it's transported over the BFC bath here. Meanwhile, it's cooled from the bottom by heat sinks with a beer cold ethanol and from the top by nitrogen vapor. And after the transfer to the solid phase, the frozen blood is cut to form plaques and is transferred in storage containers. Here we can see the current state of the float freezer, what we have in our institute. Here on the left, the liquid nitrogen tank. So first, the liquid nitrogen flows through this hose, then through the evaporator, and which evaporator leading into the freezing chamber through this 4 nitrogen hoses. And by using this infusion pump, we can control the flow rate of the water-based suspension. In this study, the first prototype of the float freezer has already been tested, and the basic control system, as you can see here, has been further developed. Here we see the new circuit built in a fuse box and a safe box. At the outside of the circuit, an automatic fuse was connected to the main supply in this series with an inductor LED, whereby this provides production in case of high currents and can be used as a main switch. The implementation of the safety measures provides a safe and virtually hazard-free handling of the electronic competence on the part of the users. Here we can see the freezing process. First floats the solution on the bath, then here's it frozen. And after that, in the further work, it will be cut and is transferred in a storage container. As you can see here, the current temperature profile in the freezing chamber. After about 1 hour, the bath has been set with constant temperature. The temperature above the BFC bath is minus 35 degrees Celsius and below minus 32 degrees Celsius. After achievement, constant temperature was the cooling rate within the solution here, 0.7 Kelvin per minute, which is still too low for us. To sum up, we have showed in this study successfully experiment certification of the first prototype for a continuous cryopreservation using the floating process and achieved constant temperature within freezing chamber at minus 35 degrees Celsius. And in addition, the control system of float freezer has been further developed to be safe and functional for human-machine interaction. The next steps are to lead up to higher cooling rates in order to subsequently store the frozen product, for example, at minus 196 degrees Celsius, and of course, by using high cooling rate. And after that, after the technical development, the freezing protocol of blood, as well as thawing protocols for the blade-shaped frozen blood have to be default. So thank you very much for your attention. I look forward to our discussion and great exchange here. Thank you.
Thank you so much for your presentation. It looks quite complicated for pure biologists as I am, but I hope that everyone will enjoy this presentation
it's a bit technical. It's a bit technical more than.
Yeah, but biology. Still, it's very important topic. So we need to know about new approaches that comes to this field. So
exactly.
The first question for you is about from Brian Grout. How do you deal with the problems of contamination from the environment?
Yeah, that's what we do now. That's like test how it's work, how we freeze the blood. Okay, then after that it will be in closed container. The process would be closed, and the blood will just drop in the freezing chamber, and then float in the freezing bath, then transferred in the storage container directly in the liquid nitrogen. So we don't have to touch or to do something. This is like automatically process, and we can keep it and avoid contamination inside the freezing chamber. In freezing chamber, we don't have to become any contamination inside the freezing chamber.
So it's
and it will be the process maybe in a safe place, or like a safety cabins, but a big room maybe, and we can avoid the contamination then. But that's the next step is like when I finish.
You are just on preliminary results, initial observation. And another question, isn't minus 35 degrees in freezing chamber is too hot? Probably you need to try to minimize the temperature to reduce it even more, but as I guess you are planning to do it in future.
Yeah, it's hard now to get a high temperature inside the freezing chamber. Regards a lot of reasons. Firstly, for example, we use now pre-fluorocarbon, and this type of pre-fluorocarbon it's have a burr point, but at minus 50 degrees Celsius. So we can use more or higher temperature. But there's another type we can use it. So we can use like the burr point by minus 120 degrees Celsius. So, for example, that's because we need the pre-fluorocarbon, keep it fluid to transport the blood above the pre-fluorocarbon what we have.
Thank you so much for your answer. And we probably have the last question for you because we are running out of time. The question is from Natalia.
It's very interesting from the point of view of physical processes. Your work is devoted to the first stage of the cryopreservation process. Do you try to cryopreserve cells, blood cells? Correct.
Yeah, already. It's blood. We already tested blood to freeze blood, but in this study not. We just tested a solution like the same like blood. So we used solid sodium chloride at the same like density of blood, and is compatible like as blood. But the first test, when we achieved the technical development and finished, then we can test the blood. We can now use a lot of blood just to test the device. But when this device is finished already, technical, so we can